Good afternoon, everybody. Welcome to the latest IRIS Core Programs webinar. This is Andy Frisetto, your host, broadcasting live from the IRIS Incorporated Research Institutions for Seismology headquarters in Washington, D.C. For those of you out there who are not familiar with IRIS, we're a nearly 30-year-old consortium of universities and also a science facility that is funded by the National Science Foundation to operate programs enabling Earth scientists to perform a broad spectrum of geophysical research, particularly related to seismology. Myself, I'm the IRIS project associate slash Swiss Army knife who helps to manage the EarthScope US Array, the Global Seismic Network, and some of the other programs and community engagement activities run by IRIS, such as this webinar series. These webinars are designed to highlight the scientific results either directly enabled by IRIS or represent important work from some of our partner organizations. So the page that I have broadcasting right now is the main webinar webpage. It's about to be actually updated into a much more efficient search page for listing these. And if you're interested in either webinars that we've done in the past or ones that might be scheduled for the future, you can either go to this page, which is iris.edu HQ webinar, or you can just go directly to our YouTube channel, which I have also up on the screen here. So this is the IRIS ENO, IRIS EPO, Education and Public Outreach YouTube page. And if you're interested, you can click on one of the webinars. And so this is one of the most recent ones, and watch away. So with that, if there's any questions about that, please email me and let me know. And so just the ground rules for the webinar today. The only people that you're going to hear speaking are myself and the presenter. If you have a comment or a question as the webinar is unfolding, you should just go to the webinar control panel that you have on your screen, sort of floating around as part of the GoToWebinar. And there's a question box near the bottom that you can type your question into. And I will see these questions streaming in during and after the webinar. And what I'll do is, after our presenter's finished, I'll go through and read your question and your name, unless you don't want me to, and you should say that. And then the speaker will answer those. If there are similar questions, I may combine some of those, or I may ask the first one and then skip the remainder. One other thing to keep in mind, if the webinar crashes, and this has actually happened once, I'm capable of rebooting it. So what you should do is just wait a second and then click on that same link that you used to access the webinar in the first place. And so we should be able to pick up like nothing happened. And also, just as a survey, I like to know if you're out there watching, if you're with a group, one of you please just send me a note and let me know how many of those of you are in the room together. It helps me know sort of the combined webinar viewership total for any given presentation. Okay, so with that, I want to introduce today's speaker. It's Professor Andy Nyblade, who is a faculty member at Pennsylvania State University. Andy has been a major contributor to the IRIS community, in particular with its polar seismology efforts, as well as efforts in Africa. He's also been a driving force, particularly in the AfricaArray program, which is relevant to today's talk. So without further ado, I'd like to introduce Andy, who is going to present on imaging the African superplume using AfricaArray data. Is the superplume a whole mantle structure? And Andy, I'm going to shift control over to you right now, and just recall that there'll be a brief hiccup. So change presenter to Andy Nyblade. And Andy, you should be unmuted now.
Okay, I think I'm here.
Okay,
Can you
great.
hear
Yep,
me?
I can hear you.
Yeah. Okay, well, welcome everyone to this webinar, and a special welcome to, I think, some folks who are watching in South Africa, colleagues and students at the University of Witwatersrand. I think have dialed in and are watching, so a very special welcome to them. I'm just coming off a cold, and so my voice is a bit raspy. I hope you can hear me okay and make out what I'm saying. I'd like to start by thanking the very many people that have contributed to the research that I'm going to present in this talk. And I can't possibly list everyone who's assisted with us over the years, but I do want to mention the students and postdocs and research affiliates that have been here at Penn State at various times. I'll just quickly read their names. They're on the front page here. Obria Adams, Brian Bagley, Maggie Benoit, Mulugeta Dudga, Sam Hansen, Audrey Huerta, Jordi Julia, Gabriel Malibo, JP O'Donnell, Young Chao Park, Angela Roish, and Fred Tugume. And then there are very many others that have contributed to this research over the years in very many African countries, and I've listed those countries. And again, I apologize, I can't possibly give everybody's name, but they come from the countries listed but here: Botswana, Cameroon, Democratic Republic of Congo, Ethiopia, Ghana, Kenya, Namibia, Nigeria, Malawi, Mozambique, South Africa, Tanzania, Uganda, Zambia, and Zimbabwe. So I want to answer or address this question: is the superplume a whole mantle structure today? And to start with, I think I'll back up a little bit and talk about what the superplume is from a historic perspective. I'll mention some of the research that has been done, or review some of the research that's been done on the superplume over the last 20 or so years, and then address the question why it's important, why the structure is, what the significance of the structure is. Then I'll segue and talk a little bit about AfricaArray and tell you what it is and talk about some of the data sets we've collected. And then from there, I'll get into our research and what our contribution is to answering this question. So let's move on here to the first slide. And my slides aren't advancing. Oh, there we go. Okay. So going back to the early 1990s, when the first global tomography models, well, they came out in the mid 80s, but this is a picture of an early model from the Harvard group in the early 90s, showing variations in wave speeds through the mantle, and the picture is illustrated such that the core is shaded with a globe here, and this white line represents the location of this cutaway through the mantle. And so if we want to see what structure looks like under Africa here, then we go to this area here, which is the core mantle boundary under Southern Africa, and then on up to the surface. So from the very earliest global models, we realized it was recognized that there is a low wave speed region shown here underneath Southern Africa that is quite large and represented a first order feature, seismic feature in the lower mantle under Africa. Let's see, my pictures are not advancing here. Is that, okay, there we go. So also about the same time in the early to mid 90s, we started looking at topography on the African continent, and it was well recognized that the anomalous plateaus in Eastern Africa and Ethiopia continued to the south into the Southern African plateau here. And we were curious about whether or not this topographic feature encompassing much of the African continent was confined to the continent or not, or whether it extended offshore into the surrounding ocean basins. So we constructed this map showing anomalous elevation on the continent and anomalous bathymetry in the ocean basins around Africa. And from this map, we argued that the anomalous elevations in Eastern and Southern Africa extended into this area of the South Atlantic, if I can find my pointer here, the South Atlantic Basin in the Cape Basin area, and that the entire topographic feature, anomalous topographic feature, was much larger than what we just saw on the continent, but actually extended into the ocean basins. And the entire combined area then we termed the African superswell, which comprised both the eastern and southern African plateaus and the area of anomalous bathymetry in the southern Atlantic Ocean. And we recognized that this large topographic anomaly was situated above this lower mantle feature that was recognized in the early tomographic images. So marching forward a decade, to 2002, 2003. These models were published by Grand and Ritzman Allen. Global models again with slices cut away here to illustrate the African superplume. This model by Grand shows two slices, A going in this profile here and B in that profile there. So the ends of these profiles show the low wave speed region of the African superplume. The bottom of these images is the core mantle boundary. The top is the surface of the planet. And you can see the low wave speed region here in the lower mantle, the African superplume, as well as is in the Ritzman Allen model over here. Now, from these images, there was a suggestion that the low wave speed anomaly in the lower mantle extended through the mid mantle here and possibly connected with anomalous upper mantle structure beneath Eastern Africa. So these models the global models have improved, marching a decade forward again to 2012. This is a representative image from Simmons et al. Showing again the same slice is shown over here, sorry, which I should have mentioned, that cuts across from Southern Africa through Eastern Africa into the Arabian Peninsula. And so this low wave speed structure here, which became known as the superplume, you can see with some greater detail in this newer image. Still with the suggestion that there's a connection between this lower mantle, mid-mantle structure and the anomalous structure in the upper mantle here beneath Eastern Africa. In addition to the tomographic images that were being developed, a number of researchers were looking at the propagation of various seismic phases through and around the sides of the superplume structure. This is one such paper by Ni et al. In 2002. And in this work, they looked particularly at S and SCS phases, the paths shown here in red, the S turning above the core mantle boundary and the SCS coming here along the core mantle boundary, propagating through the low wave speed structure of the African superplume. Now, for the synthetics that they generated using just the model from the tomographic image, produce these wave shapes here. This is what the data look like with both the S and the SCS phases. And so in order to get a better waveform match in this modeling exercise, they put in a lower wave speed region with minus 3% a reduction in the shear wave velocity in this area that's outlined in green, and this area has a very steep sides. So from this and similar kinds of efforts by others, it's been argued that the superplume structure has to be not just a thermal structure, but also a chemical structure. There has to be anomalous chemistry, and so it's really a thermochemical feature in the lower mantle, not just a thermal anomaly that's creating the low wave speeds. Additional work along the same lines done by these authors using different ray paths in different phases that sample the lower part of the mantle and the core mantle boundary region within and around the superplume. And again, in these papers, the very lowest wave speed region near the core mantle boundary was mapped out with greater detail as shown here, as well as looking at the structure as it extended up into towards middle mantle depths. And with these studies, again, the goal was to constrain the shape of the structure and figure out how far this structure extended towards the mid mantle. Now, while these studies were going on using seismic data and looking at the seismic structure of the superplume, the geodynamics community was looking at trying to understand the geodynamic structure of this feature and how it might have come about. And one of the earliest papers to address this was by Anderson in 1994, who argued that the superplume structure in the lower mantle sits here beneath Southern Africa in this area that hasn't been perturbed by or experienced subduction since the breakup of Pangea. So the areas here that are shaded show Jurassic to Eocene subduction and then Permian to Triassic subduction in the shaded area here, and this area in between has not experienced any subduction. So the suggestion was made that the superplume structure in the mantle was somehow related to an area of the mantle that hadn't been disrupted or hadn't experienced penetration of subduction slabs deep into the mantle in this part of the globe. Other models that were soon thereafter published that combine this idea of a thermochemical structure into chemical or compositional stratification in the mantle were shown here. This is a paper by Kellogg et al. In 1999 and McNutt, where the superplume structure extends some distance up into the mid-mantle, and then thermal instabilities along the sides of the structure give rise to smaller thermal plumes that then rise towards the surface and then are expressed at the surface as hotspots. A number of other researchers also looked at the development of thermochemical plumes or structures in the mantle using tank experiments. So here's some pictures from some papers doing thermochemical convection in a tank. And in these particular experiments, superimposed layers of two miscible fluids, different viscosity and density, were stuck together in the tank and then cooled from above and heated from below to see what kinds of thermochemical structures might develop. And in cartoon fashion here, which illustrates what's happening actually in the tanks over here, you can see these large structures, thermochemical structures rising from a stratified boundary near the core mantle boundary up towards the mid-mantle, and then possibly giving rise to smaller plumes, thermal plumes that emanate from the surface of these larger thermochemical structures. Geodynamic modeling was also extended to look at how, moving forward again here into the mid-2000s, looking at how the large thermochemical structures both beneath Africa and a similar structure that's near antipodal beneath the South Pacific, how these structures could have come about by having a heterogeneous layer at the base of the mantle that gets pushed around or swept into piles by mantle convection driven by sinking slabs. So here are the results from that McNamara and Zong's paper in 2005. The images here show different input of different thicknesses for the basal layer. That's the DI number here, from 127 kilometers to almost 1,000 kilometers in thickness. And these geodynamic models then are driven by plate motions over the last 119 million years, looking at where the slabs have penetrated and looking at how the lower mantle structure gets swept up or pushed into piles, and then comparing the structures here to what's actually seen in some of the global seismic models, the model here by Grand and the seismic model here by Ritzma. These models were extended in this paper by Gennaro, McNamara, and Lay in 2008 to look more carefully at the thermal structure around these piles, these thermochemical piles in the lower mantle. And so in these cutaways here, you can see the thermochemical structures near the core mantle boundary, and then the thermal instabilities around the edges of these piles that give rise to thermal structures that then rise up towards the surface and are manifest as hotspots at the surface. So taking this and turning it into cartoon fashion here, in this image we have the large thermochemical pile beneath Africa shown here, thermal instabilities around the sides of this structure giving rise to smaller thermal plumes that then rise to the surface, for example, as shown here beneath East Africa or Africa, and then also over here with this antipodal structure beneath the Pacific. Other geodynamicists have looked at what might happen if these thermochemical structures rise through the entire lower mantle and impinge on the 660 kilometer discontinuity, which is widely regarded by many to be a barrier to flow in the mantle. And so in these two papers, the effect of a thermochemical plume impinging on the 660 kilometer discontinuity have been imaged or have been modeled, and in this case you can see the plume coming up here, pancaking out against the 660 and then heating the base of the transition zone, which then gives rise to thermal instabilities that then go up to the surface, is manifest as smaller thermal plumes. The same can be seen in the picture from the paper by Campbell. Let me take a break here. My voice is getting raspy. So through the 90s and 2000s, we were focused on imaging the upper mantle structure beneath Eastern Africa, which was known to be anomalous, but to the extent to which it was anomalous, we were uncertain. But we conducted seismic experiments starting in the mid-1990s in Tanzania, so a 20-station deployment here, and then in 2000 to 2003, deployments in Kenya and Ethiopia, and many additional experiments, temporary networks have been deployed since then. So the focus of these studies were to image the upper mantle structure and to determine what the origin of the rifting, the Cenozoic rifting, and volcanism and plateau uplift were with respect to upper mantle dynamics, and whether or not there was a connection with what was happening dynamically in upper mantle beneath East Africa with what was happening in the lower mantle beneath Southern Africa. So some of the, in cartoon form, some of the models we were testing were an edge flow model where you have a thermal gradient set up here by thick cratonic lithosphere juxtaposed with thinner mobile belt lithosphere, creating a convection system that looks like this. So in the case of East Africa, this would be the Greater Congo Craton over here. This would be the mobile belts, the Proterozoic mobile belts in East Africa, and convection forming in this fashion. Other models also that have been proposed over the years for understanding the rifting and volcanism in East Africa are shown here. The classic passive rift model where the lithosphere is stretched, and the stretching induces a small scale flow in the upper mantle underneath the area where you have thinned lithosphere. Multiple plumes have been invoked to explain what's happening with the rifting and volcanism in East Africa over the years. So in this cartoon, there's 3 separate plumes shown. Some people have argued just for one, others have argued for 2. And then finally, in this 4th diagram, we show in cartoon fashion what the upper mantle might look like if it's connected through the transition zone across the 410 660 to the lower mantle beneath Southern Africa. So if we look at the images that we were able to obtain from these networks in Tanzania, Kenya, and Ethiopia, there's slices shown through here for those models going from the surface down to various depths. This goes from the surface to 500 kilometers beneath Ethiopia, 0 to 300 beneath Kenya, and 0 to 500 beneath Tanzania. And in all of these images, we were able to map or image perturbed upper mantle structure, shown by the red colors here, the low wave speeds. But the aperture of these networks were such that we couldn't image very far into or below the transition zone. So these models all end at depths of 3 to 500 kilometers, which is the depth extent to which we could resolve structure. So with these images, we were able to argue that the perturbed upper mantle structure beneath Eastern Africa extends from the very shallow mantle down into the transition zone, across the 410 and into the transition zone. But whether or not there was a connection with the lower mantle, we were not able to determine. So the unresolved question then is, does the anomalous lower mantle structure under Southern Africa connect across the mid-mantle to the upper mantle structure beneath Eastern Africa? And you might say, well, who cares? You know, why is this important? Why does it matter whether those structures are connected or not? And the answer is, it really, at least in my way of thinking, is fundamental to understanding how the mantle works. We've known for a long time, since the mid-1990s, that slabs penetrate in some places into the lower mantle. For example, this picture from Grand et al. In 1997, where you can see the Farallon plate here mapped out quite well, extending below the transition zone down well into the lower mantle. So as shown here in this cartoon fashion, we know that in some locations, maybe not this one against South America, but in some locations the slabs extend well into the lower mantle. And at the ridges, the upwelling is shallow and passive. So we have a first order mode of circulation in the convection system, represented by the downgoing slabs in the lower mantle. But what is the nature of the return flow from the deep mantle, or is it not? Is there no major form of return flow? So downgoing at the slabs, where is the return flow coming? And in this cartoon from Anderson et al., that's expressed here in what he calls the plume model, where beneath Africa and the Pacific, you have a large-scale structure in the lower mantle that's rising towards the surface, and that represents a first-order return flow of warmer mantle material that is juxtaposed with the cold sinking slabs as illustrated here. Now, what happens to these structures and whether the structure is through going or not is really the issue. And if the African superplume or the Pacific superplume is continuous from the core mantle boundary to the surface, then that certainly could possibly represent a first order form of return flow in the mantle. So I want to shift gears a bit here. Let me get some water and talk a little bit about AfricaArray and the data sets we've collected, and then get back to the African superplume. So AfricaArray started really in October 2003 when Paul Dirks, who is the head of the School of Geosciences at the University of Witwatersrand in Johannesburg, asked me if I had any ideas about how to help him revitalize or rebuild the geophysics program at WITS. So we put together a bunch of ideas and with the idea of not just focusing on WITS and the geophysics program at WITS, but scaling up a program that would support capacity building in geophysics across the African continent. So our goal was to establish right from the beginning a public-private partnership to support capacity building and research in geophysics in Africa with an initial hub or focus at WITS, but then extending out to other universities and organizations across the continent. And then we had even grander designs. If we thought if we could do this in geophysics, then perhaps we could promote capacity building more broadly in all of the geosciences and all the related fields of the geosciences. So AfricaArray got underway officially in 2004 after our initial meetings with a commitment from 3 founding partners: Penn State, the University of Witwatersrand, and the Council for Geoscience, which was formerly known as the Geological Survey of South Africa. And early on, we had important critical support from IRIS in various forms to help us get started. We chose the name AfricaArray. I guess we pirated it a bit from US Array, but the significance of the name is a bit different in that we weren't just looking at building an array of scientific observatories, but we also wanted to build an array of training programs, research programs, arrays of partnerships and collaborations. So we took the name Array to be used broadly. And as the initiative has gained momentum and we've grown over the years, it's really come to be broken into 3 different parts. Shown here, there's a network in Africa that is comprised of seismic, GPS, and weather sensors. There's both an undergrad and graduate research and education programs in Africa at WITS and other African universities, as well as in the US. And all of this has been funded by project-based funding to make it happen. So just a snapshot of some numbers of what we've achieved so far. The supports come from lots of different organizations, and we like to recognize that support and acknowledge that support. It's been critical for what we've done. The National Science Foundation in the US has been absolutely critical in providing funding, as has the National Research Foundation in South Africa. WITS, Penn State, and the Council for Geoscience, the founding partners, have also contributed substantial resources, and then we've obtained support from lots of corporate sponsors as well as many other government organizations. On the education side, we've had lots of students that we've supported, over 50 BSc honors students at WITS. These are 4th-year students specializing in geophysics at WITS. 18 master students have completed their degrees, 12 PhDs, and we've supported 7 postdocs. And in the US, we've had a program focused on diversity in the geosciences, and there's been 54 students, undergraduate students, over the years involved in that. We currently have 6 BSc honors enrolled at WITS. There's 7 master students in the program right now, 9 PhDs, and 3 postdocs. The network, I'll show you a map in just a second, 51 observatories in 19 countries, and we've also operated many temporary seismic networks over the years. And our partnership base has grown, broken out here in terms of different organizations with the numbers shown, universities in Africa, universities elsewhere, government organizations in Africa, and then government organizations elsewhere, companies, and then finally academic endorsements from academic and industry societies. Here's a map of the observatory network. 51 stations now in 19 countries. 48 of those stations have seismic stations, seismic equipment. The seismic only are the white triangles. Co-located seismic GPS and weather stations are shown with the blue symbols, and then just co-located seismic, the dark blue, and then the purpley color here is the GPS only, a couple GPS only stations. We record continuously. Our data recovery has been between 70–80%, and the data is available through IRIS for the seismic data and UNAVCO for the GPS and weather data. Data retrieval, some stations have been online, and we're getting more stations online either through cell modem telemetry or directly connected to the internet. But many of the stations are still standalone stations, and someone has to visit them every few months to download data. Just show a few pictures here of what some of the equipment looks like. Whoops, go back up here if I can. Okay, there we go. It's a large image file. So this is showing a couple of permanent stations. This is a station in Ghana. That's that station right there. It was a former WWSSN station, and this building, the basement of this building is a nice pier, and you can see the old WWSSN seismometers. So sort of 1960s era seismometry, 1970s era seismometry, and then the new GRAL 3T seismometer that we installed at this station. This is a picture from this station, Tezi in Zambia. That's that station right there. This was a vault that was built in the 1970s on a dam. The dam was never completed, but the vault for a seismic station is still there. We were able to reoccupy the station with a nice concrete pier in it with our seismic equipment. And then at the surface, we have our high-tech solar panel mounts, as you can see here. And then at this station, we have co-located GPS. There's the GPS antenna and then the weather sensor there. So that's what some permanent observatories look like. The temporary networks, as I mentioned, we've run many of these over the years. You can see what happens here. We dig a pit in the ground, install the seismometer. Solar panels usually go on a roof nearby, and then the sensor and the data logger and batteries are covered in barrels, drums here, and then the equipment is buried. And then we return once in a while to service the stations and download data. So the networks we've run, focused in East Africa, are shown in this map. As well as the previous networks. So from 2007 to 2011, we operated stations in this configuration in Uganda and northern Tanzania. The 20 stations here that were installed for 18 months, and then the equipment was removed and redeployed to southern Tanzania, the red diamonds here, this location, and then after 18 months they were removed again and redeployed into the purple pink locations in Zambia. We also installed and operated stations in these locations in Tanzania in 2010 and 2011. The previous deployments in the area are shown here, the stations that I showed before in Tanzania and Kenya, as well as data from the CRISP experiments in Kenya in the 1985 and 1989, 1990. So we've used data from all of these stations, the temporary stations, as well as the permanent AfricaArray stations, as well as the GSN stations operated by IRIS in Africa, to probe mantle structure using very different methods. And I want to now get back to the African Superplume and talk about some of our results and what we're finding. Excuse me. So the first study I want to highlight is one published by Hansen et al. In EPSL in 2012, where we developed, or I should say, Sam developed a global model using the MIT global model from Rob Vanderhill's group, which involves an adaptive parameterization of the grid, so that where you have great array coverage, you can use a finer grid and pull out better resolution. So Sam used this method with all of the data available from Africa and combined with the global data. So the data that goes into the global data sets are shown by the red symbols, and the data arrival times for P waves that Sam added are shown with the blue symbols. And as you can see, that tremendous data coverage was improved tremendously throughout Eastern and Southern Africa by the data that was added in the model that I'll show you in a second. So here's the cutaway of the model through the African mantle. And the top panel shows the slice through the model at 150 kilometers. The uppermost mantle in this model is not very well resolved, but you get down in the transition zone and deeper, it's better resolved. But this figure anyway shows where the slices are. You can see AA prime here. That is this slice down here. So the model goes from deep in the mantle. It's not right at the core mantle boundary, but deep in the lower mantle to the surface. This is Southern Africa. That's this area here, East Africa. This area here, Ethiopia, right there, and then into Arabia over here. The 410 and the 660 kilometer discontinuities are shown, and the areas with slower wave speeds are shown with red, and faster are shown with blue, as is standard for these models. So you can see the low wave speed structure of the Superplume here beneath Southern Africa, extending through the mid-mantle, coming up to the base of the transition zone here, and then in this image connecting with the upper mantle structure across Eastern Africa. So in the prior models that I showed you, there's always a resolution issue of whether or not this area of the mid-mantle could be well enough imaged to really say whether there was a connection beneath the structure here in the lower mantle with the structure in the transition zone. And if we look at some depth slices in the checkerboard models for this particular image, we can see that the horizontal resolution is actually quite good. These are checkerboard results. So these are resolution tests at 900 and 1150 kilometer depth. So we've used the same data, the same array path coverage, the same travel times to try to see what sorts of checkers we could recover, and you can see that these are pretty well recovered, indicating that the horizontal resolution in this model is pretty good. Laterally, you can see that the checkers, especially throughout Eastern and Southern Africa, are fairly well resolved. However, the issue really is the vertical resolution with these models, and so what we've done is we've done a number of vertical resolution tests to probe the vertical resolution, and the results the tests I'm showing you here are ones where we've put a low wave speed blob structure in the lower mantle to represent the lower mantle structure of the Superplume, and then a perturbed area in the upper mantle to represent the perturbed upper mantle structure beneath Eastern Africa. And then we've separated them by different distances, so having unperturbed mantle in beneath them of various thicknesses, and then run this through the code with the data to see what we could actually recover. And these are the structures over here that we can recover. So if there's a large separation between these two, we certainly can resolve the two structures independently. But as these structures become closer and closer together, they start to smear together. And if there's only a few 100-kilometer separation between these two structures, then certainly they can smear together. So here's what we image, and given these results, we can say that the lower mantle anomaly has to rise to a depth of about 1,100 kilometers, which is somewhere right in here. But whether or not there's a gap in between there and the base of the transition zone, we can't really tell. So if a separation exists between the lower mantle structure and the upper mantle structure, this gap can only be on the order of a few 100 kilometers in order to satisfy the data. So that's where we are with looking at this problem from a global perspective with a global model. We've also worked the problem from the top down using a regional body wave tomography, and in this particular study done by Gabriel Mulibo for his PhD thesis, he used the Van de Kar inversion method for travel time inversions of P and S waves. And now to get a good image, you need good azimuthal coverage. And this figure here shows the event locations that were used for both the P and the S model. This is the P model here, the S model on this side. And you can see that there is really excellent azimuthal coverage. We have travel times, rays coming from all different directions to the networks in Eastern Africa, providing very good resolution. So here, the P and the S model are very similar, and so I'll only just show you the S model to illustrate the main features that are resolved in these images. These are depth slices at 100, 2, 3, 4, 5, 600 kilometer depth. The middle part, this is the outline of the Archean Tanzania craton, which sits in the middle of East Africa. The eastern branch of the rift system's here, the western branch is over here. And what we see is that at shallow mantle depths, the low wave speed region is confined to the rift system itself, primarily around the craton. But then when we get down to deeper depths into the transition zone, the low wave speed region coalesces beneath the middle of the craton and underneath the center of the entire East African plateau. Looking at this in cross section, B to B prime goes like this. Here is B to B prime. And we can see the fast structure of the craton in the middle, the western branch over here, the eastern branch here, and we see this low wave speed structure extending. I keep losing my cursor here. Let me go back. There it comes back again. You see the low wave speed structure extending from shallow in the mantle through the transition zone in these images down into the lower mantle. So we can ask the same question, what is the resolution of these images? And the lateral resolution is good, shown by this checkerboard image here. So here are the checkers, and look at this profile through here. You can see the sides of these checkers are very well resolved, but there is vertical smearing, which is the problem with body wave tomography. If we do the same sorts of tests as we did with the global model, and we put a lower mantle structure in and an upper mantle structure shown here, and change the distance between these two structures and see what we can recover, this is what we recover. And again, even in these models, if there's a few hundred kilometers, only a few hundred kilometers separating these two structures, the structures smear together, and maybe that's what we're seeing here. So even with these, with the regional model, we still are left with this possibility that there may be a small gap in here of a few hundred kilometers beneath the lower mantle structure and the upper mantle structure. So we can't rule out two separate structures with that. So we turn to a third study, and that's using looking at the transition zone and the topography on the transition zone discontinuities to look to see whether there's a temperature anomaly that exists at the mid-mantle in that area where the tomography would allow for a separation. So to do this, we look at the two major phase transformations in the olivine system in the mantle, the 410 kilometer and 660 kilometer discontinuities. And at these phase transformations, we do have seismic discontinuities, and those discontinuities we can image by looking at converted phases, P to S converted phases from those discontinuities using receiver functions. So in the case where the mantle transition zone has higher temperatures or is warmer than normal, the Clapeyron slopes of these discontinuities are such they're opposite, such that the 410 is depressed and the 660 is elevated, and the transition zone, the distance between these two discontinuities, diminishes. That's the opposite in areas of higher temperature. And so with receiver functions, we can look at the positions of these discontinuities by mapping out P to S conversions on both of these interfaces. So we've done that. This is a map showing the location of the P to S conversions at a depth of 660 kilometers to give you a sense geographically of the distribution of the pierce points or the conversion points. We've stacked these receiver functions and converted to depth using our 3D velocity model that I just showed you, excuse me. And I'll just quickly show you the results here. And we'll focus on this profile here, BB prime, that cuts across from Zambia through Tanzania and into Kenya. So here are the results from the receiver function stacks, and this is the profile BB prime. Again, these are the S models that I showed you before at 660 kilometer depth and the cross section. And looking at BB prime, we go from an area in Zambia, southern Zambia here, across the Western Rift, across the Tanzania Craton and into Kenya. And here are the receiver function stacks. So Zambia, down in this area here, we see the 410 and the 660 at the right depths, unperturbed. We come close to the Western Rift here. This area here, we see the 660 rises, the 410 is depressed. That depression continues on the 410 clear across into Kenya. The 660 stays elevated till we cross the eastern branch of the rift system that's over here, and then we get into northern Kenya, and the 660 goes back to the right depth. So clearly an indication that the transition zone is thermally perturbed. There is actually a dramatic thinning here. You look at this profile A to B, or A to A prime rather, and you see the same structure, the thinning of the upwelling or the upwelling, but the shifting upwards of the 660 discontinuity, and then the depression of the 410 kilometer discontinuity. If we map out those thicknesses in transition zone, it's shown here, and we find this big swath through this area, Zambia, through central Tanzania into Kenya, where the transition zone is on the order, on average, between 220 and 210 kilometers, compared to the global average that's somewhere between 240 and 250. Down here, over here in Zambia and to the north here, we find normal transition zone thicknesses. So the area of perturbed transition zone is in this swath, a few hundred kilometers wide and a couple thousand kilometers in length. So it's a long, broad area of perturbed transition zone. So the summary of findings, the coincidence of the thin transition zone with the low velocity anomaly across the mid-mantle really, we believe, provides compelling evidence for a whole mantle structure. And it's not a thin structure, it's a broad connection across the mid-mantle. Now the evidence we have from the results I just presented would indicate a thermal structure. We're only looking at temperature variations, and those temperature variations are on the order of a few hundred degrees. If you look at how thin the transition zone is. So the question is there evidence for actual flow across the 660? If the structure is a thermal structure that continues from the core mantle boundary to the surface, is there actually flow across this boundary? So this is a model of a plume from a paper by Ewan et al., where the plume pancakes out against the 660, heats the bottom of the transition zone, and gives rise to smaller thermal structures that then rise to the surface. So is this a possibility? Is the superplume pancaking out against the 660 and just heating the transition zone, and which would be consistent with our seismic results? Or is there any evidence for actual flux of material across that boundary? And we can look at this in two ways. I'm going to speed up a bit here so I don't run out of time. We can use seismic anisotropy or shear wave splitting results to try to map out the flow direction in the upper mantle to see whether there's any consistent patterns that might be indicative of flow from deeper in the lower mantle. Now, with shear wave splitting, we can, if we have an incidence shear wave on an anisotropic medium, the shear wave will be split or polarized into a fast and slower wave, and we can measure both the polarization direction as well as the splitting time between those two waves. Now, the classic interpretations of these results fall into three groups. The fossil anisotropy has often been attributed to anisotropy in the lithospheric mantle from olivine that has been deformed and strained during large-scale deformation, such as mountain building episodes. Lithospheric mantle flow will also result in a preferred alignment of the olivine crystals, giving rise to a fast shear direction, a polarization direction, and this can be from plate motion or from other reasons. Or you can get seismic anisotropy from fluid-filled cracks within the lithosphere. This would be, or if you want to think about this as shape anisotropy, that's another way to think about it. So we have used our results to determine shear wave splitting, the fast polarization directions, and the splitting times for all of our data. And this is published on paper by Bagley and myself. And we've used the method of Silver and Chan for making the measurements, and the stacking method of Wolf and Silver. So here are the results. And what we find if we start in Zambia is a fast polarization direction represented by the alignment of the blue lines. That's more or less in a northeasterly direction in northern Zambia. The shear wave splitting bifurcates, the directions bifurcate around the southern part of the Archean Tanzania craton, this structure right here, and they continue up the sides and wrap around the top part of the craton here and around and up this side, the eastern side of the craton here, and then continue into Ethiopia and all the way into the Arabian Peninsula. Now there's different ways to interpret this and different interpretations that have been proposed for different parts of these data sets. So we've combined our data sets, our data measurements here with other data, other measurements that others have made, for example, in Kenya and in Ethiopia. And in some of those papers, fluid-filled cracks in the magmatic sections of the rifts have been invoked, which is a possibility, but that doesn't work for areas where there isn't any magmatism. So the bulk of our measurements here and down here in Zambia, there is no volcanism. So magma-filled cracks in the lithosphere doesn't work. Plate motion is not aligned with the fast polarization direction. Here's the absolute plate motion for Africa. Here it is for Saudi Arabia. It's not consistent with the fast, this generally northeast fast alignment. So plate motion doesn't seem to be a satisfactory explanation. Fossil anisotropy is a possibility for many of these measurements, but not all of them. We can explain all of the measurements around the edge of the craton here by looking at the collision directions of orogenic belts against the craton, and you could explain all these measurements with that around the edges, but you can't explain these measurements here in along the northern edge of the craton in Uganda. So I've taken this area and I've blown it up here, and these measurements here are particularly important for this interpretation because there's a shear zone here, the Aswa shear zone, and they cut across that shear zone. You would expect if the fabric, the anisotropic fabric from the shear zone would create a fast polarization direction that was parallel to it, not orthogonal to it, as we see here. And also the Ruwenzori belt, a Paleoproterozoic mobile belt that sits right here, its convergent direction against the craton is north to south. And again, that would create more or less east-west splitting directions, not north-south. So these measurements here can only be explained by a large-scale flow field in the upper mantle. And so if we look for one explanation for all of the seismic anisotropy, that one explanation that is consistent with all of the observations, we can invoke a large-scale flow field that is illustrated here on this structure, on this figure that shows a cutaway of the seismic image I showed you earlier, with the low wave speed region beneath the lower mantle coming up beneath Eastern Africa here in the transition zone. Now, in this suggestion of this flow field is that the warm material arises through the lower mantle, crosses the transition zone beneath Zambia right here, and then continues to the north beneath all of Eastern Africa and the Arabian Peninsula. Now, to create the seismic anisotropy that we see here, this flow field must bifurcate and be channeled around the thicker lithosphere of the Archean craton, which is shown here, and in the seismic anomaly, that's this blue area right here. So the flow comes up, it moves around, beneath and around the thick lithosphere of the craton, and then continues to the north. So this explanation can explain all of the shear wave splitting directions, and particularly these measurements right here in northern, along the northern edge of the Tanzania craton. So I know this is an IRIS webinar, but I'll take the liberty anyway to show one slide with some geochemical data. This is a figure from Hilton et al.'s paper showing helium isotope ratios for Eastern Africa. And helium, these high helium-3, 4 ratios have long been argued as a geochemical fingerprint of deep mantle connection. So the measurements, these high helium-3, 4 ratios in Ethiopia have long been known, been documented in literature. In this paper, Hilton et al. found high helium ratios also in this volcanic province in southern Tanzania, the Rungwa volcanic province, indicating that there was a possible connection with deep mantle structure in this part of the East African Rift System, as well as to the north in Ethiopia. So that is consistent with our model shown here, where Rungwa sits right at that point right there, where this upwelling is coming from the lower mantle into the upper mantle, and then continuing to the north. So so in support then there of flow from the lower mantle into the upper mantle, there's these two arguments. One is the helium data, and then the other is the seismic anisotropy, which can be interpreted with a large-scale flow field connected to the lower mantle. So let me wrap things up. In conclusion, the first conclusion, the African superplume is a whole mantle feature, at least a thermal feature in the mantle, maybe not a thermochemical plume that extends all the way from the core mantle boundary to the surface, but a thermal structure that extends from the core mantle boundary all the way to the surface. And the connection across the mid-mantle between the lower mantle structure under southern Africa and the upper mantle structure beneath eastern Africa is not a thin connection, it's a broad connection. So it's not as shown in this cartoon here, where you have a dense thermochemical structure that's giving rise to instability, one or just a few instabilities that rise through the transition zone thinly and disturb the transition zone thinly, but it's a broad disruption to the transition zone. So is it, as suggested in this model here, is this structure coming all the way to the 660 and flattening out and perturbing thermally the base of the transition zone, which then gives rise to smaller plumes? That's a possibility. Or is there flux right across the 660 all the way to the surface? That's another possibility. The second conclusion is that the superplume may represent a large-scale return flow in the mantle, coming back to why this is important, and that cartoon I showed you before from Anderson's paper. This structure does come up to the 660, and thermally it does extend into the upper mantle, so there is a thermal connection again. Whether there's actually flow, material flow across this interface, I think is not at all clear, but nonetheless there is a thermal structure that rises through the entire mantle and may represent then a large-scale return flow that complements the large-scale downgoing that's associated with slabs at some of the subduction zones. And the same can be said for the structure in the South Pacific. Okay, so there's still many things we need to know. Here are a few questions that come to mind. How does the compositional heterogeneity affect the density-driven flow? How much of the structure is compositional? How much of it's thermal? How do those two components act to control the buoyancy of the feature? Where does the excess heat and/or the anomalous chemistry come in from within the structure come from? And thirdly, why does the structure tilt toward the northeast in the mid-mantle? Is it part of a large-scale flow field, perhaps related to the subduction of the closing of the Tethys and the Tethys subduction system? I think it's a wide open question. And then lastly, how much mantle flow is there across the 660 discontinuity? Is this structure just a thermal connection across the 660, or is there actual flow across that discontinuity? So I'll stop there, and hopefully there's a few minutes left for some questions.
All right, thanks very much, Andy. There's definitely room for questions. It's not like we're in a seminar room and we have to get out because a class is coming in. So we definitely have time to go through what's been submitted, and there's already several questions in my window here. I just wanted to say thank you. That was a really interesting talk, and there's a lot of cool results coming out of AfricaArray. So it was great to hear over here. I want to thank everybody in the audience who was on the listening end. And if you're all right with this, Andy, I'll just start going through the questions.
Sure.
Okay, great. So the first question / comment is from Gust Nolet, and he asks, Isn't it more likely from a dynamic point of view that slabs and plumes would have each their own return flows close to the location where they transit the 660? Return flow is probably adiabatic and difficult or impossible to see in tomography.
Well, I guess, I'm not a mantle geodynamicist, so there are probably others that are better equipped to answer that. What I will say is that this is a large scale structure and extends from the core mantle boundary, as I mentioned, all the way to the surface as a thermal feature. So if it doesn't represent part of the return flow in the mantle convecting system, then what is it? Um, you know, there's probably different modes of convection, and certainly a return flow mode that's localized to each subduction system and each slab sinking is a possibility, but the slabs that are penetrating all the way through the transition zone into the lower mantle, what happens to the large scale circulation that's related to those? I think that's the issue. If the slabs are not penetrating through the transition zone, then certainly the flow field, the upflow that would be associated could be more local. But I think in some instances, certainly there's good evidence that the slabs penetrate well into the lower mantle, and so what happens? What sort of return flow is associated with that? Uh, maybe the superplume isn't part of a return flow, but it's certainly a large feature, one of the largest features in the mantle, and it certainly looks like some sort of at least a thermal upwelling, and the bottom part of it may be maybe a strong chemical component to it too. So if it's not part of the return flow system, then you can turn the question on end and say, well, what is it? How does it fit into the larger circulation of the mantle?
All right. Next question is from Luciana Astes, and she had two questions, and I'll just ask them together. One was, what is the network code in the DMC for Africa Array?
Okay, the permanent stations are AF. Uh, Again, that's AF for the permanent stations, and the temporary stations, the ones that I showed you through Uganda, Tanzania, and Zambia are ZP. That's a temporary network code. Uh, those data are all open. They were part of Pascal project, so the data was initially embargoed for 2 years, but that data is all open now, uh, as is most of the AF data.
And then a related question from Luciana was, is a station installed by the IMS in Zimbabwe part of the network?
No, no, we have a station right next to the IMS station.
Okay. Next question is from Ling Chen, who is curious, what are the variations in lithospheric thickness in East Africa?
That's a tough question. I think it's tough to answer anywhere exactly how thick the lithosphere is. Um, we think underneath, the best estimates underneath the Tanzania craton, which is an Archean lithosphere, is on the order of 150 to 200 kilometers. Uh, in the tomographic images I showed, the fast structure, lithospheric structure of the underneath the craton gets smeared to deeper depths. So it appears as though the fast structure extends down to 300 to 400 kilometer depth. But other seismic imaging methods, as well as constraints from xenoliths, indicate that the lithosphere is probably on the order of 150 to 200 kilometers beneath the Archean Tanzania craton. Excuse me, I'm losing my voice here. Excuse me. Beneath the rifted mobile belts, it's certainly thinner than that. How thin? It's probably highly variable, um, uh, depending on a number of factors. But it could be on the order of 70, 80 kilometers, maybe in some places, and 100, 120 in other places. It's not well known. Uh, I think it could span quite a range of thicknesses. In Zambia, if you get further south and away from the rifts into unrifted Proterozoic terrains, again, my best guess is somewhere 100 to 150 for the Proterozoic lithosphere, but again, it's not well constrained. it's not well known.
Okay, thanks, Andy. Next question is from Jennifer Jenkins, and she asks, several recent studies have indicated a more complex nature to the 660 discontinuity. She refers to double peaks being observed and possibly the greater importance of a garnet phase transition at a similar depth to the spinel perovskite transition. Do you see any evidence of this in your receiver functions, or do they all follow the normally predicted lowered 410, raised 660 for hot areas?
That's a good question. Yeah, we do see some evidence if we go to higher frequencies. The receiver function stacks I showed were pretty low frequencies, but if we compute our receiver functions with a higher frequency content, um, in some places there's indication of a second converted phase coming in that would correspond to around 7-10 kilometer depth that would possibly correspond to the garnet phase transformation. Uh, so, but it's not, we don't see that consistently everywhere, just in some places in some of our data sets.
All right. Next question is from Januka Ataniake, and Januka asks, "How can you tell if wave splitting is due to active deformation or the result of a relic petrofabric?"
That's a that's a conundrum. Everyone has their favorite answer for that. Uh, I think most people they look at the tectonic history of an area and see whether the fast polarization direction is consistent with the mantle fabrics that might have been developed during ancient orogenic events, or if the fast polarization direction could be consistent with the development of shape anisotropy in the lithosphere from fluid-filled cracks. Um, in our case in Eastern Africa, what I showed, I mean, you could invoke multiple explanations. You could invoke fossil anisotropy, excuse me, in the lithosphere. In some places, other places, you could invoke magma field cracks. Other places, you could invoke flow in the sublithospheric mantle to explain the direction. So you could piece together a variety of explanations. So we're not denying that. What we're arguing is that if you look for one consistent explanation, one explanation that can explain all of the observations, the only one that we know of right now is this large-scale flow field in the sublithospheric mantle associated with the superplume flow. Is that okay?
Okay. And sort of a related question from Sarah Stamps, who is curious, at what depth do you expect the anisotropy of Bagley and Nyblade to originate?
It would be sublithospheric depths, and again, if the lithosphere has variable thickness, then it would be that would vary, but on the order of maybe in the areas where the lithosphere may be thinner, 70 to 80 kilometers and deeper, and maybe other places 100 kilometers or 120 kilometers and deeper. Uh, uh, so that's as best I can tell. It has to be, in our model, it's sublithospheric mantle flow, and so it has to be below the lithosphere, however thick the lithosphere is.
Okay, great. A couple questions that I'm going to bundle together from both Ling Chen and Ayub Kaviani that are curious. Do you believe there is any connection between the African superplume and the generation and evolution of thermal upwellings in Northeast Africa, such as the Afar upwelling and also the opening of the Red Sea?
Yeah, we certainly think in this, if there's a large scale flow field going from south to north through Eastern Africa, as I illustrated in that one picture, uh, then certainly the whole Afar area, Ethiopian Afar, is part of this large scale flow field. And we puzzled about that. If you look at the seismic images for Afar in Ethiopia, the the amplitude of the signal, the amplitude of the anomaly rather, is much larger. You see the reddish blob is much redder and larger beneath Ethiopia and afar than elsewhere. And in a paper that Sam Hansen and I wrote this last year, published last year, we argued that in Ethiopia and afar, one possible explanation for that is that you have a combination of this of the warm material that's flowing in a northward direction, giving contributing to the seismic anomaly. And then on top of that, you have a zone of partial melting, decompression, or partial melting in the uppermost mantle underneath the rift system and afar that is also contributing, and you have this combined effect to slow down wave speeds then from the partial melting, the presence of partial melt in the shallowest part of the upper mantle, and then this larger scale flow field of warm material that extends to deeper depths in the upper mantle. And if you put those two together, then you end up with a larger seismic, larger seismic anomaly beneath the Afar in Ethiopia than you do elsewhere. So that was that's a possible explanation for why you see variability in the seismic structure of the upper mantle along strike in Eastern Africa, going from the south to the north.
This is another question that's kind of related to that I didn't notice when I asked the last one, but I'll ask it just the same. This is from Christelle Wouthier, and she's curious: how do you reconcile a south to north main mantle flow with the rifting ages, where the older, more mature parts of the rift are towards the north?
That's a good question. There was a paper published by Eric Roberts and others a year or so ago, and they presented new dates for volcanic material in southern Tanzania around the Rungwa volcanics, the dates of 22 to 24 or 25 million years, if I get the dates correct, which indicates that the rifting in southern Tanzania may be a lot older than we previously thought. So the literature the results in literature indicate from previously that the rifting in the Western Rift has been much younger, say starting 10 to 12 million years ago. But the results from Roberts et al. Indicate that may be not so, that the rifting may have been much older. So I'm not so 100% sure that there is this north to south or south north to south age progression in the age of rifting. Certainly maybe locally within the Kenya Rift, coming through Kenya and into northern Tanzania maybe, but that could just be within that portion of the Eastern Rift. And the Western Rift, there's a south to north progression where the rifting in southern Tanzania is much older, and then as you go to the north and in the west along the Western Rift, it becomes younger, which would be just the opposite. So I think the I think there's more to be learned about the timing of the rifting. I don't think we know the full story yet. Excuse me, I'm losing my voice.
Andy, you're a total trooper for doing this while still sick, so I really appreciate that, and I'm sure everyone else does too. There's only a few questions left, if you
Okay,
can hold out.
I'll see if my voice holds out here.
Okay. There's a question from Daniel Lau Davila at Oklahoma State, and he's asking, what are the implications for the edge-driven convection model?
Um, we think that the perturbed structure in Eastern Africa is much too deep and extensive to be explained by edge-driven convection. Um, Certainly, the connection through the transition zone, to the base of the transition zone down into the upper part of the lower mantle, you can't explain that by edge-driven convection, which is a smaller scale convection confined to the upper mantle. So I don't think that there could be a contribution from edge-driven convection, but I don't think it can't be the full story. There's got to be a deeper connection to the lower mantle.
Okay, question from Min Chen. Has any sort of azimuthal anisotropy study been done in this part of Africa?
There there are surface wave papers that have been published, some by our groups, using surface waves to look at anisotropy. Excuse me, and the results are variable. I don't think it's very well constrained. Excuse me, I'm losing my voice now. Uh, uh, we think that the results from the shear wave splitting are more indicative of anisotropy, what's going on. Um, there is an indication that there is from the surface wave studies, there is a north-south fabric, uh, which you can see at different periods if you do the inversion of the surface wave data for different periods. Excuse me, but it's not as robust a result as we're getting, we think, from the shear wave splitting analyses.
Okay, great. I have two questions left, and I will cut it off at that if you're okay with that, Andy. If there's any
Yeah,
more, I'll
that's
just proceed.
yeah. I know people can email me. I'm happy to answer emails.
Okay. Yeah. Why don't we just do that? Why don't we have a Sarah Mana and a Mouse? If you just want to send those notes to Andy, I can. If he wants, he can CC me when he responds, and I'll put them on the YouTube page, just so that you can go have some hot tea or whatever, or a lozenge or whatever you need.
I'm out of water here. I'm
Yeah.
out of
Okay.
water.
Well, yeah, I really appreciate it, Andy. It was really interesting, and it was a great overview of all the great work that's been going on in this part of the world. So much appreciated. And for everybody out there, also, and I should note, Andy, there were lots of I didn't read them because they weren't questions, but there were lots of positive comments from people who thanking you for the talk. So yeah, if anybody else has any questions, why don't you just email them to Andy? And if there's a way to get the answers back to the webpage, we can do that. And our next webinar will be in a couple weeks, so look for those emails. And thanks again, Andy.
Okay. Well,
And
thanks to everybody for listening.
no problem. Feel better and take care.
Thank you. Bye.
Bye.